Alright, hello everybody. So today we're talking about partial fraction decomposition. So our first question today is, what is 2 over x minus 1 minus 1 over x plus 2? Right, so we need to know how to combine these two fractions. That's our first question. So whenever we're trying to combine two fractions, they need to have the same denominator. So I'm going to multiply both sides of this by x plus 2 and both sides of this by x plus 1. So this is equal to 2 times x plus 2 over x minus 1 times x plus 2 minus, and then for this one, we're going to multiply both sides by x minus 1. So we're going to get x minus 1 over x minus 1 times x plus 2. Okay? And then now they have the same denominator. That was our goal. So now that they have the same denominator, we can combine the numerators. So we've got 2x plus 4 minus x plus 1 over x minus 1 times x plus 2. Right, what I did here was I distributed that minus sign. And then you can just combine like terms. So here you're going to get that this is equal to x plus 5 over x squared plus x minus 2. Right, so if you FOIL the denominator, that's what you're going to get. Okay. So now we can ask the question, suppose I ask you to solve the integral of x plus 5 over x squared plus x minus 2 dx. Right? So we don't quite know any methods to solve this integral, but if you look back at what we did up here, we said that this fraction is actually equal to this fraction minus this fraction. So we can just rewrite this integral as the integral of 2 over x minus 1 minus 1 over x plus 2 dx. Right? So now we can break this into two fractions, so we can take the integral of this minus the integral of this. And now you try to solve these two integrals, and you say, well, we can actually solve these, right? So we can try u substitution, and that's actually going to work here. So if we do the u substitution, I'll write here u substitution. Right, so if we do the u substitution, then this is going to be equal to 2 times the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 2 plus c. Okay, so the way we solved this was by first breaking it into two different fractions and then taking the integral of each fraction using u substitution in order to get to here. Right, and I'd encourage you to do the work here to fill this in, but this is what the answer should be. Okay. So let me say here in a different color, the method of breaking down a rational function right, a rational function is just a function that's a fraction, right? So a rational function into simpler parts or simpler fractions is called partial fraction decomposition. we'll abbreviate it PF. Right, so partial fraction decomposition is just what we did here, where we have this fraction and we break it into two simple fractions, right? So what we did was actually the reverse of that. We started with these two and got to here. But if we were given this integral, we'd have to work backwards and get up to the two simple fractions. Okay. I'll say here, note partial fraction decomposition only works if the degree of the denominator is bigger than the degree of the denominator, or of the numerator. Right, so we saw here the degree of the denominator was bigger than the degree of the numerator, so we were able to use partial fraction decomposition. Okay, so let's go ahead and do another example here. We'll just go ahead and flip to the other board. So, example number 1. Let's say we have the integral of x over x squared plus x minus 20 dx. Okay, so we're trying to take this integral. And again, we want to use partial fractions to try to decompose this into a simpler thing. So notice here we've got, so I'll rewrite the fraction that we have. So we've got x over x squared plus x minus 20. I'm trying to do partial fraction decomposition. So that's the fraction we have. And, excuse me. Right, so the thing to notice here, let me use red. The thing to notice here, well, let's try to factor this. That's what I meant to do first. So if we try to factor the denominator, we're going to get x over, so we need two numbers to multiply to give us negative 20, but when their difference, the difference between them needs to be 1, right? So if we think of two numbers, we can think of two numbers that are 1 apart, but multiply to give us that number. So it's probably going to be 5 and negative 4, right? So it's going to be x plus 5 times x minus 4, because here 5 plus negative 4, that gives us the 1, and then negative 20 is 5 times negative 4, right? So that's how we would factor that. So x over x plus 5 times x minus 4. And I'll say here, the fact that we have two factors, here are two factors, means that our answer is going to have two fractions. And I'll say here that this is important. Right. So you have to look at how many factors are in the denominator, and that's how many fractions you're going to get. So what this tells us is that our answer is going to be a over the first factor plus b over the second factor, right? So that's how we're going to decompose it, just a over the first factor plus b over the second factor. And now we want to combine these two fractions. So the way we can combine these two fractions is to say, well, I want these two to have the same denominator, so I need to multiply both sides of this by x minus 4, and multiply both sides of this by x plus 5. Or if you drew a picture of what's going on, I'm multiplying these two things as well as these two things, right? So you just multiply those things together. So if you do that, you're going to get a times x minus 4 plus b times x plus 5 over x plus 5 times x minus 4. Right. Okay. So that's just how you would combine the two fractions. And then we can go ahead and distribute. So if we do that, we're going to get ax minus 4a plus bx plus 5b over our x plus 5 times x minus 4. Okay. So now we have to look back at our original function. So we said the numerator of our original function is x, and the numerator here is this complicated thing that we've written down. So this numerator, since the denominator is the same, this numerator is the same thing as x. So I'll say here, now look back at original function. Right, so if we look at the original function, we're going to get the original top. The original numerator was x, and that's equal to the thing that we just found. So ax minus 4a plus bx plus 5b. Okay. So now we actually want to combine like terms. So if we're going to do that, then we're going to say that x equals, so if we combine the x terms, we're going to get a plus b times x. And then if we combine the constant terms, we're going to get this minus 4a and this plus 5b. So we're going to get minus 4a plus 5b. Okay. So just combining like terms, that's how we get there. And the thing to notice, x is equal to this side. So what we can say is, well, this constant part must be 0, and this coefficient must be 1, right? Because it's equal to x. So the coefficient of x must be 1, and this must be 0, and this gives us two equations. So our equations are going to be a plus b equals 1, and minus 4a plus 5b equals 0. Okay, so we want to use one function to solve, so whenever we're trying to solve two functions at the same time, we need to solve one of the functions for one of the variables and plug that into the second function. So what I'll do here is say this means that b equals 1 minus a, and we can plug that into here. So we're going to get that minus 4a plus 5 times 1 minus a equals 0. Now we can try to solve for a. So we're going to get 5 minus 4a minus 5a equals 0. So 5 equals 9a. So a equals 5 over 9. Right? So that's how we would get that. So a is 5 over 9. We plug that into this equation. So b equals 1 minus 5 over 9, which is 9 over 9 minus 5 over 9. So we're going to get that b equals 4 over 9. Okay. So all this work here, all the stuff in red and green and black here, all of that is just to figure out what a and b are equal to, right? So we got a is equal to this number, and b is equal to this number, right? So this fraction is equal to this, but we've just found out what a and b are, right? So we can plug that in. So we can write here, so the integral of this fraction, x over x squared plus x minus 20 dx equals, well, we said the fraction was actually equal to this, and we found what a and b are. So it's going to be equal to the integral of
5/9 over x plus 5 plus, and then it would be b 4/9 over x minus 4 dx, right? So I'm using the fact that this fraction is equal to this, and we found what a and b are to get to here. Right, and from here you can actually just use u substitution. So I would break it into two different integrals, and then I would use u substitution. So equals ... So this is u substitution. And your answer is going to be 5/9 natural log of the absolute value of x plus 5 plus 4/9 natural log of the absolute value of x minus 4 plus c. Okay, so that's our answer. Now, notice what we had to do here with this part in red and green and black here was to figure out what a and b are. And that was kind of a difficult process because we had to solve two equations at the same time. But now let's try to find a different way to figure out what a and b are. So let me say here, so let's look at, which equation was it? Right. So we know that this numerator here, this box here, is equal to x. Right, so we know that this numerator is the same thing as x. So I'm going to rewrite that on the other board. So we've already solved the problem, but I just want to show you a different way of doing that part of the problem. So we know that, let me erase this first. Okay. So we know that x equals a times x minus 4 plus b times x plus 5, right? So that's the equation that I wrote down on the other board that I just rewrote here. This is true for all values of x, right? So if we make a smart choice for our value of x and just plug it in here, we can actually just solve from this equation exactly what a and b have to be equal to, right? So let's just try to be clever about our choices of x here. Well, notice if you set x equal to 4, this part goes away, so that's probably helpful. So if you set x equals 4, then we're going to get that x equals, so this part goes away, so it's b times, we said x was 4 plus 5, right? So here we're going to get that, we also know that x is 4, right? Let me just write the whole thing out. That's what I meant to do. Alright, so if we use this equation, we plug in x equals 4, a times 4 minus 4 plus b times 4 plus 5. Right, so I just plugged in 4 up here, and now we can see that this part cancels out, so 4 equals 9b, and that gives us exactly that b is 4 over 9. Right, and we can solve for a similarly, because if we try to get rid of this part by setting x equal to -5, and what we get here is going to be that -5 equals a times -5 minus 4 plus b times -5 plus 5. So again, this part is going to go away, and now we're going to have -5 over -9, so a is 5 over 9. Right, so instead of doing that part where we solve two equations at the same time, we can just kind of guess values of x that will make this more simple for us to solve for a and b. Okay, so that probably seems a little bit complicated, so we should just learn how to do that in another example. So let's do that. Let me erase this board. Okay. So the next example is going to be, so number 2 is going to say the integral of 2x over x cubed minus x squared minus x plus 1 dx. Right, so notice here that in the denominator, well, first we have to figure out whether we can use partial fractions, but the degree of the denominator is bigger than the degree of the numerator, so we can use it. But notice, in order to factor the denominator, we're trying to factor a trinomial. I'm not going to make you do that on the test, but the way we would factor this trinomial is to say that this x cubed minus x squared minus x plus 1 is going to be equal to, we can factor it as x minus 1 times x squared minus 1. And we can actually factor x squared minus 1, right? So that's a difference of squares, a squared minus b squared. So this is a difference of squares, so we can write this as x minus 1 squared times x plus 1. Okay. So we figured out how to factor the denominator. So I'll write that here. So we know that 2x over x plus 1, so our fraction is equal to this. Right, so this fraction in the integral is equal to this fraction. This is just factoring the denominator. So we get here. Okay, and now we want to decompose this. And remember what I said earlier, here we've got actually 3 factors in the denominator. We've got an x plus 1, and we've got 2 copies of x minus 1, right? So we're going to have 3 fractions because we have 3 factors in the denominator. Okay, so the way we're going to write this is going to be a over x plus 1, right? So that was our first factor, plus b over x minus 1 to the power of 1. Let me actually use a different color here. So x minus 1 to the power of 1. That's a 1. Plus c over x minus 1 to the power of 2. Okay. So notice here, this is just, we copied down the first factor, that's how we do it. And then notice here, this is squared. So the way we deal with powers in the denominator is we just keep writing each factor. So let me write that down in a separate note, or as a separate rule. So let's say here, rule, if x minus 1 to the power of 7 is in the denominator, then your partial fraction decomposition will include, it'll be a over x minus 1 plus b over x minus 1 squared plus, and then you just keep going until you get to eventually g over x minus 1 to the power of 7. So the way we deal with repeated factors is we just keep on listing out these fractions for each power of this repeated factor. So in this case, this was to the 7th, so we had 7 different fractions corresponding to this factor right here. Okay, so that's what we did up here. We had 2 copies of this x minus 1, so we wrote down x minus 1 to the first power, and then here we wrote down x minus 1 to the second power. And that's how you deal with higher powers whenever you add those into the denominator. Okay, so this is just a separate rule that we'll use later. And now we can go ahead and write down what this means. So we know that 2x equals, okay, so if you want to combine all of these fractions, what you have to do is multiply both sides of this fraction by, you want this denominator to match this denominator, so you need to multiply both sides of this fraction by whatever this denominator is, remove this factor, right? So this denominator is x plus 1. What's missing is this x minus 1 squared. So we're going to have a times x minus 1 squared, right? And here we've got b over x minus 1, but here we have x plus 1, and we've got 2 copies of x minus 1. So what's missing is 1 copy of x minus 1 and 1 copy of x plus 1. So we're going to have plus b times x minus 1 times x plus 1. Okay, and then we look at the final fraction. If we want this denominator to look like this denominator, we need to multiply both sides by x plus 1. So we're going to have plus c times x plus 1. Right, so this is just what you have to multiply each of these numerators by to get or each of these fractions by to get the denominator to look like what you have on the left there. So that's the equation that we get. So this numerator here is going to be equal to this thing on the right side. Okay, and now we're going to try to go ahead and guess values of x that are going to make 2 of these terms cancel out. So notice, let's just say, well, you might want to pause and think about what values of x would work here. But let's say you set x equal to 1. Then notice this term goes away, and this term also goes away. So that's what we're going to do first. So let's say if x equals 1, then what we're going to have is going to be, so if you plug in x equals 1, you're going to get 2 equals 2 times c. So you just plug in x equals 1 everywhere here, and this is the equation that you're going to get. And that means that c is equal to 1. Right, so we've already solved for one of our variables. Okay, the next thing we're going to try here, we're going to see, well, how can we get these 2 terms to go away? And the answer is if we set x equal to -1, both of these 2 terms go away. So let's say if x equals -1, then what we're going to have, once those 2 terms go away, is going to be -2 equals a times -2 squared. That's just by plugging in -1 everywhere here. Okay, so this is what we get. We divide by 4 on both sides, so we're going to get that a equals -1/2. Okay, and lastly, so we know what a is, we know what c is, we just need to pick some value of x, and then just plug in a and c, and then we can get b. So I'll just pick an easy value of x. Let's say here x equals 0. Okay, so if x equals 0, then the left side is 0, and the right side is going to be a times -1 squared plus b times, this will end up being -1, plus c times, well, 1. Okay. So this is what we get, and we can say here, well, this is just 0 equals a minus b plus c. And now we can just plug in what we found for a and c. So we're going to get 0 equals, what was that? So it's -1/2 minus b plus c. Right? So c is 1, right? So we got to figure out what we need as b here. So we just subtract, so 1 minus 1/2, that's 1/2. So if we then add b to both sides, we're going to get b equals 1/2. So I'll just write down here what we found out. We found out that A was equal to negative 1/2, B was equal to, what did we say, 1/2, and C is equal to 1. So that's what we just figured out on this right side here. So now I'm going to erase that so that we can do the rest of the problem. Okay, so we just figured out what A, B, and C are. So we know that the integral of 2x over x cubed minus x squared minus x plus 1 dx, well, we said that it's actually equal to this sum of fractions. And we actually just figured out what A, B, and C are. So we're going to go ahead and write that this is the integral of A, negative 1/2, over x plus 1, plus the second fraction was 1/2 over x minus 1, and the third fraction was 1 over x minus 1 squared dx. Okay, right, so the hard part of these are just figuring out the values of A, B, and C. Once we figured that out, we can now just go ahead and solve all of these integrals. So the way we're going to solve all three of these, so we can just separate this into three integrals. The way we would solve all three of these integrals is by u substitution. So I'll say u substitution. So do your u substitution, and your answer is going to end up being 1/2 natural log of the absolute value of x plus 1 plus 1/2 natural log of the absolute value of x minus 1 minus 1 over x minus 1 plus c. And this is our answer here. Okay. So now we want to do our third example. Okay. So let me write that down. Okay. So example number 3 is going to be the integral of x squared minus x plus 12 over x cubed plus 2x dx. Okay. And I'm just going to write down here a useful formula. Right, you're not expected to remember this, but just a useful formula for this problem is that the integral of 1 over x, I'm sorry, I meant to write x squared plus a squared dx equals 1 over a times the tangent inverse of x over a plus c. Okay, so we're not going to use that immediately, but I'm just going to say later on we're going to need that formula in this problem. But first, we need to factor, right? So we're going to factor the denominator. That's the most important thing to do first, just so that you can know what you're working with. So if we factor our denominator, we just rewrite our numerator. But if we factor our denominator, you just think about what term, or what can you factor out of both terms, and you can factor out x. So you can write this as x times x squared plus 2 dx. And you can't factor this any further, because if you go ahead and let's say you tried to use the quadratic formula, you would get a negative number inside of the discriminant, right? Or the discriminant would be negative is what I meant to say. So you get a negative number inside the square root. So this is just, right, the other way of seeing it is x squared has to be negative for this to be 0, and the only way for that to be true is if x is a complex number, right? So this can't be factored any further. Okay, so this is our factorization of the denominator. So we can say here that, let me use a different color here, x squared minus x plus 12 over x times x squared plus 2. I want to decompose this into a list of fractions. But I'll say here, whenever you have a quadratic that cannot be reduced, you're going to have to do something a little bit different. So that's what I'll do here. So for the first term is the same as we've been doing. So we're just going to have a over the first factor x plus, now we write our fraction with the second factor of the denominator. But whenever you add this fraction with this quadratic irreducible polynomial, whenever you add this, you're going to have to make the numerator something slightly different. So you have to make it bx plus c. So once again, just whenever you have a quadratic you can't reduce, that's when you have to make the numerator that different thing. And in this case, it's bx plus c. Okay. So now that we've done that, we can say that, let me figure out what color I'm using. So the numerator on the left is equal to, so now we're just trying to combine the two fractions. To combine the two fractions, they have to have the same denominator. So you need to multiply both sides of this by x squared plus 2. So a times x squared plus 2. And to make this denominator the same as this, you need to multiply both sides by x. That's not what I meant to write. Well, yeah, that works. X times bx plus c. Okay, so you need to multiply both sides of this by x to have the same denominator, so that's why I wrote that. Okay, and now you need to just distribute everything. So we're going to have a times x squared plus 2 times a plus b times x squared plus c times x. And just rearranging everything, we're getting a plus b times x squared plus c times x plus 2 times a. Okay, so you look at here, this is our quadratic term. This has to be the same as this quadratic term. Our linear terms have to match up, so this c times x has to be the same thing as negative x. And also, the constant terms need to match up. So this 2 times a better be the same thing as 12. Right, so that's actually going to give us what all of our constants have to be. So here, this first one tells us that a plus b equals 1. So we know a plus b equals 1. Our second one, the one in green, tells us that c is equal to negative 1. And the one in orange tells us that 2a is 12. Which means that a is equal to 6. All right, so if we plug in a equals 6 up here, then we're going to get that 6 plus b equals 1. So then we get that b is negative 5. Okay, so we found all three of our constants. This is b, this is c, and this is a. Right, so we found all of our constants. Now we can just plug those in to this fraction and rewrite our integral. So if we do that, we're going to have the integral of x squared minus x plus 12 over x cubed plus 2x dx equals, now we just rewrite it in this form. We have a, which is 6 over x plus bx plus c, so that's negative 5x plus c, so minus 1, over this x squared plus 2 dx. Okay. So now we can say, well, let's just separate this, because we know how to work with something of the form 1 over x squared plus this constant, but we need to separate this into two parts in order to get one part that looks like that. So if we do that, then we're going to get the integral of 6 over x minus 5x over x squared plus 2 minus 1 over x squared plus 2 dx. Okay, so now you can break this up as 3 fractions. So you got, let me just write this. This is going to be 6 times the integral of 1 over x dx minus 5 times the integral of x over x squared plus 2 dx minus the integral of 1 over x squared plus 2 dx. Right, so for here, we're going to use, for this one, we're going to use u substitution. And for this one, we're going to use the formula that we wrote down at the beginning. Right, so if you just use the formula for this one, and you use u substitution for that one, then what we're going to get as our answer is going to be 6 natural log of the absolute value of x minus 5/2 natural log of the absolute value of x squared plus 2 minus 1 over root 2 tangent inverse of x over root 2 plus c. So I encourage you to fill in the gap here that I left between this step and this step, but this should be your final answer here. Okay. And now let's do example number 4. Okay. Example number 4. We're going to have the integral of 2x squared plus 7x plus 2 over x squared plus 1 squared dx. Okay, so let's go ahead and write down here. I'll just rewrite the fraction. Notice x squared plus 1 cannot be reduced any further. That's an irreducible quadratic. So notice whenever we're trying to break this up as separate fractions, remember what we did in example 2 was we said that whenever we have repeated denominators, we have to write first this denominator to the first power plus the second fraction would be this denominator to the second power, right? So that's what we did in example 2. I wrote down this thing in red that told us exactly what to do whenever we have repeated factors in the denominator. We just write down each part like this. Okay. The next tool we need to use is what we talked about in example 3. We've got this irreducible quadratic. And I said whenever we have an irreducible quadratic like that, what we need to do here is rewrite this as ax plus b, and rewrite this part as cx plus d. Right? So the reason why these are linear terms instead of just constants in the numerator is because these things in the denominator are irreducible quadratic polynomials. Okay. And now we can actually go about solving this. So 2x squared plus 7x plus 2 equals, okay, so now we want this fraction to look like what we have here. It's got exactly one copy of x squared plus 1. It needs another copy, so we multiply both sides by that. So we're going to have ax plus b times the x squared plus 1. And if we look at what we have here, this denominator already matches this fraction, so we can just write down here plus cx plus d. We don't have to multiply it by anything because this denominator already matches what we have on the left there. Okay. Now we need to FOIL this out. So if we do that, we're going to get, so multiply the first two terms, we get a times x cubed. So we're doing FOIL, so first, then outer, so multiply the outer terms, a times x, the inner terms, b times x squared, and then the last term, so b times 1, plus cx plus d. Okay. And now we can just collect like terms, right? So we can rewrite this as, let me just rearrange things. If I rearrange things, then we're going to have a times x cubed plus b times x squared plus c times x, or sorry, plus a times x. No, that's not what I meant to write, sorry. Plus a plus c times x is what I meant to write, plus b plus d. Okay, so I just combined these two terms here to get this. So I just combined all of the like terms so that now we can see clearly what's happening. So notice on the left we don't have any cubic terms. So what should this coefficient be? Turns out this coefficient here should actually be 0. Because here, if this thing is anything other than 0, then you should have a cubic term on the left, which you don't. Okay, the next part here, if you look at this b times x squared, here b times x squared needs to be the same thing as 2 times x squared, so b equals 2. Okay. Sorry. Okay. So the next part here, a plus c times x needs to be the same thing as 7. So we know here that a plus c is 7. And here, b plus d needs to be the same thing as 2, so we know that b plus d equals 2, but we already know what b is, so 2 plus d equals 2, so d should be equal to 0 actually, right? And we actually already know what a is, so 0 plus c is 7, that gives us that c is 7, right? So we found a, b, c, and d, right? Okay, so I just looked at the left to figure out what each of these coefficients should be, and then just solved for each of the variables. So that's how we get these numbers here. Okay. So now we can say that our original integral, which was the integral of 2x squared plus 7x plus 2 over x squared plus 1 to the power of 2 dx is going to be equal to the integral of, now we just plug in a, b, c, and d into this form. So we've got a is 0, b is 2, so 2 over x squared plus 1 plus, and then now for this part, cx plus d C is 7, D is 0. So 7x over x squared plus 1 squared dx. Okay. So here we're going to have to use that formula that I wrote down in red the last time. So we just break this into two different integrals. For the first one, we have to use the formula that I wrote down last time, in the last problem rather. And for the second one, we can just use u substitution. So if we do that for both of these, then what we're going to get is going to be it's going to be 2 tangent inverse of x minus 7 over 2 times x squared plus 1 plus 7. Okay, so that's going to be the answer for that. Okay, so let's just do a bit of a recap. So what to look for? So we have to say, are the denominator factors linear or quadratic? Right? So if it's a linear factor, that means you have just a number. So just a in the numerator. And if it's a quadratic factor, you're going to have something like ax plus b in the numerator. Okay, so that's what you have to look for there. And the other question is, are any denominator factors repeated? And if no, then that means that factors appear once in the decomposition, in the partial fraction decomposition. If yes, then what that means is, if, let's just say, what should I say here? If factor appears k times, then it appears in k fractions. Right, so an example was, let's say you have something like, let me use a different color here. Let's say you have something like x squared plus 1 to the power of k. Then what you have to do then is write something over x squared plus 1 plus something over x squared plus 1 squared plus, and then you just keep going until you get something over x squared plus 1 to the power of k. Right, so you have to add together k of those fractions. Okay. So let's just go through a few examples of how we would do this. Right, so for all of these types of problems, just the more examples you go through, the more familiar it will become. Well, actually, let's first just write down what we did in examples 1 through 4. So, in example 1, what we did was we said we have x over x plus 5 times x minus 4. And using the rules there, what we have to write is going to be a over x plus 5 plus b over x minus 1. Alright, so I encourage you to stop the video and think about each of these. But the second one, 2x over x plus 1 times x minus 1 squared. Think about what you should get on the right side. And what it's going to be is x plus 1, x minus 1, and x minus 1 squared. And this was a, b, and c. For our third problem, we got x squared minus x plus 12 over x times x squared plus 2. And if we try to decompose that, well, we have two factors, right? So we've got something over x plus something over the second factor, which was x squared plus 2. And pause the video, think about what the numerator should be. But the numerator here is going to be a, and the numerator there, since it's an irreducible quadratic, needs to be bx plus c. And the fourth one was 2x squared plus 7x plus 2 over x times x squared. That's not what I meant to write, sorry. It's over x squared plus 1 squared. So again, pause the video, think about what you should get on the right side. But this is going to be x squared plus 1. And the second one should be x squared plus 1 squared. And notice these are both irreducible quadratics, so you get ax plus b. And here you get cx plus d. Okay. And I'll just list out 3 more cases for you guys to think about. Okay. So, exercise, so exercise A. So let's say exercise, write out the form of the partial fraction decomposition. For A is going to be 2x plus 5 over x minus 2 squared times x squared plus 2. Part B is going to be x squared plus 4 over x cubed minus 3x squared plus 2x. And part C is going to be x cubed plus 3 over x times 2x minus 1 squared times x squared plus 3 squared. Okay. So pause the video here, think about what each of these should be on the right side, kind of like what we did over there. And I'll go through the answers now. So for the first one, right, so we've got one repeated factor, and we've got another factor here. So we've got in total 3 factors. So we're going to write out, this would be x minus 2, this would be x minus 2 squared, and this would be x squared plus 2, right? And then we just have to write out the numerators. So this would be a, b, and this is an irreducible quadratic, so this is cx plus d. Okay. For this one, first you got to factor it to figure out what this would be. So this is x squared plus 4 over, if you factor this, you can factor out an x, right? So I said I wouldn't make you factor a trinomial, but if it's as simple as this, you can actually just do that, right? So you just have to factor out x, right? So if you factor out x, then you factor what's left over, then you're going to get x times x minus 2 times x minus 1. And now you can write out the partial fraction. So you're going to get something over x plus something over x minus 2 plus something over x minus 1. Okay, and then here this would be a, b, and c, since none of those denominators are actually quadratics. Okay, and now you go to the third and final case here. So we already have the factors listed out. So we've got the factor of x, plus we got the factor of 2x minus 1, and then that thing squared. And I'll just write here in a second line, plus we've got our x squared plus 3, and then plus we've also got that thing squared. Right, so we've got 5 terms, I've just had to break it into 2 lines here, and we just look at each term. So this is linear, this is linear, this is linear. This thing is quadratic, so we've got dx plus e, and then so a, b, c, d, e, f, and g. Okay. Right, so that's how you would decompose all of these using partial fraction decomposition. Okay, so we've just got one last thing to quickly talk about today, and that's called rationalizing substitution. So it's just use substitution, but just a little bit different than what we'd usually do with use substitution. Right, so this is called so we already talked about partial fractions. Right now we're talking about rationalizing substitutions. So all it's doing is, let's say we have, in this case, the integral of the square root of x plus 4 over x dx. And we're trying to solve this integral. Then we can notice that, well, it doesn't really work if we set u equal to x. It doesn't really work if we set u equal to x plus 4. But what we can try in this case is u equals the square root. Right, so that's what we're going to try. Okay, so rationalizing substitutions, the time when you're going to have to pick this value of x is just whenever you've got some kind of fractional exponent. So remember, the square root is the exponent of 1/2, so this is a fractional exponent. So here, whenever you have something like this square root, that's when you might have to do this type of integration, where you pick u to be equal to this thing, right? So remember, in the trig subproblems, you don't necessarily have this. You might have like the square root of x squared minus a squared. But if you see something like that, then you know you have to use trigonometric substitution, because that's in that form. But this is not x squared minus a squared, this is just x plus 4. So here we're just going to use u substitution. We're just going to try u substitution. So this is equal to our u. But we don't know what to do with this x. So in order to figure that out, let's square both sides. So u squared is x plus 4. And let's solve for x. So x is u squared minus 4. So we actually know how to replace the numerator, and we know how to replace the denominator, but we don't know how to yet replace the dx. So what I'm going to do here is take the derivative of both sides of this. So we're going to say du equals the derivative of this, right? This is x plus 4 to the 1/2 power. So the derivative of that is 1/2 of x plus 4 to the 1/2 minus 1, which is negative 1/2, and then times the derivative of x plus 4, which is just 1 dx. Okay, so that's how we take the derivative of that, and this is what we get here. So oh shoot. Sorry, that's not what we wanted to do here. Let me just back up one step. That's not what we wanted to do. The easier way to see this is to actually just take the derivative of both sides of this. So if we do that, we're going to get dx equals the derivative of this, which is 2u du. Okay, so that's actually what we wanted to do. We take the derivative of both sides of this to get here. Okay, so now we know how to replace everything in this integral, and we're going to go ahead and do that. So we're going to take the integral of, we said the numerator was actually u, so this is u, over we said x was u squared minus 4, and we said dx was 2u du. Okay, so now we can rewrite this as the integral of, I'm sorry, this is 2 times the integral of u squared over u squared minus 4 du. Okay, we don't quite know how to solve this integral yet, but what I'm going to do here is just a little trick. I'm going to rewrite this as, that's not what I meant to write. I'm going to rewrite this as 2 times the integral of u squared minus 4 plus 4 over u squared minus 4 du. And the reason I did this is because now we can break this up as 2 fractions. So this is, let me just write over here, this is 2 times the integral of u squared minus 4 over u squared minus 4 plus 4 over u squared minus 4 du. Okay, so that's what we get there. And notice this first thing is just 1. So we've got 2 times the integral of 1 plus 4 over u squared minus 4 du. Alright, and notice now we don't quite know how to take the integral of this thing, but we can use partial fractions. So that's what we're going to do here. So if we use partial fractions to solve that thing, let me erase this. Right, so this was 2 times the integral of 1 du plus 2 times the integral of 4 over u squared minus 4 du. We're trying to figure out how to solve that integral, so we need to use partial fractions. So if we use partial fractions here, then we know that 4 over u squared minus 4 is the same thing as 4 over u plus 2 times u minus 2, which we said using partial fractions is going to be something over u plus 2 plus something over u minus 2. And since these are both linear, this is A and this is B. So now, again, we just need to make sure the right side matches what we have on the left side. So the left numerator is 4, and on the right, here we've got u plus 2. To make the fractions match, we multiply both sides of this by u minus 2. So we've got A times u minus 2. And here to make the fractions match, we need to multiply both sides by u plus 2. B times u plus 2. Right? So we now distribute. So 4 is AU plus BU minus 2A plus 2B. Okay. Yes. So what we can do now is say, well, we've got A plus B times u minus 2a plus 2b. So we know this part, a plus b, is 0, and we know this part, minus 2a plus 2b, is going to be equal to 4. So we can solve this equation for one variable. A is negative b. We plug that in here. So we're going to get 2b plus 2b equals 4. So b is 1. And then if you plug that in here, a is negative 1. Right, so we can break up this integral. So 2 times the integral of 1, that's just 2u. So now we can say, well, this here is equal to 2u plus 2 times the integral of these two fractions. So it's going to be negative 1 over u plus 2 plus 1 over u minus 2 du. And now we can just go ahead and solve this. So I'd say using u substitution, you'd use a letter other than u, because we already have u. But you're going to get, eventually, 2u plus, so 2u plus 2 natural log of the absolute value of u minus 2 minus natural log of the absolute value of u plus 2 plus a constant c. And now we just need to plug in what u was. We set u equal to the square root of x plus 4, so we just plug that in. So we've got 2 times the square root of x plus 4 plus 2 natural log of the absolute value of the square root minus 2 minus 2 times the natural log, sorry, there should be a 2 here. 2 times the natural log of the absolute value of the square root of x plus 4 plus 2 plus a constant c. So this thing here is our final answer. So this is, you have to start the problem using u substitution. You get down to this point here, and now we can say, well, we need to use partial fractions here. Well, you get to this point, and then you use partial fractions to break that thing up. You solve your partial fractions, and then now you plug it in and just do u substitution one last time to solve the rest of the problem. So that's how you would do that type of problem.